Hello students, welcome to the EN 401 lecture on soil basics. Here's the roadmap for our soil basics lecture. We're going to talk about soil formation, soil composition to include phase relationships and voids, and then we're going to use that knowledge to do some basic earthwork calculations after we talk about some terminology, and specifically we'll go into the average end area method to find the volume of earthwork. Well, why do we care about soils? And the simple answer is any facilities project is going to end up being built on or in the soil, right? So this famous piece of architecture here, the Leaning Tower of Pisa, is a prime example of what happens when you are unaware of the soil conditions or do not plan properly, right? This tower is leaning with a pretty good angle there, and had there not been some modern intervention, this tower would have eventually fallen to the ground. This link down here for the Millennium Tower is another great video. Definitely watch it. Essentially, this is the modern day Leaning Tower of Pisa in San Francisco, and the soil conditions were not fully analyzed, and this massive, expensive tower was built and immediately started to have uneven settlement sink and start leaning. So there's a multi-million-dollar restoration project to get this fixed, all because they didn't care enough about the soils. All right, so where do soils come from? Well, pretty much all soils come from weathered rock. So whether that rock is weathered via a mechanical means, right? So physical weathering, so rain, wind, snow, ice, glaciers, mechanical weathering of rock, or chemical weathering, so oxidation of the minerals in the rock, or even biological weathering. So either the plants and animals turning that rock into smaller rock particles, or also the decomposition of plants that turn into soils. So here we have some examples of physical weathering or mechanical weathering. Caused by all of these things. Big thing to note that really breaks down rock is called frost wedging. And so essentially rocks are all porous to some extent, and when those pores get filled with water and then that water freezes, the water expands, and that expanding water causes the rock to break. And when it breaks, now you have a larger void that can fill with more water, and then that freezes and that breaks the rock even more. So continually frost wedging and breaking that large rock into smaller and smaller pieces. We can also see that wind and water break down rock and turn that into soil. A great example of that in the United States is the Grand Canyon. Used to be a large plateau of limestone, and that has all been eroded and broken down by the Colorado River, and all of that sediment has been sent downriver to the Colorado River Delta, which is near Yuma, Arizona, and down into Mexico. So another way that rock is broken down is by chemical weathering. So in this photo here, we have a piece of granite, right? So the nice granite that you're used to seeing is this nice gray stuff right here in the middle, but this outside layer of granite has been oxidized, and so this oxidized granite is much softer than the non-oxidized granite, and has lots of voids. So the soft void-filled granite here is easy to be broken down by mechanical means, so frost wedging, wind, flowing water, those kinds of things. So chemical weathering really allows a rock to be more susceptible to physical weathering. And then we also have biological weathering. So in this photo here, we got all these big trees growing on the side of a hill, right? Well, these big trees grow big roots, right? So these roots can go in between the cracks and rocks and make those cracks bigger and break off chunks of rocks. We also have microbial activity, that the different types of microbes can actually dissolve the rocks. Um, so lichen is a special type of fungi and algae. They live together in a symbiotic relationship, and this lichen is known to digest and dissolve rock and turn that into soil. Also, just the breakdown of organic material into um, soil is another process that biological weathering takes to make soils. So soil composition. So with all those different means of weathering, we want to know what actually ends up in our soil. So soil is a mixture of our minerals, our weathered rocks, and organic matter. That makes up all the solid stuff, and then between all these solid pieces we have water and air. All right. So soil is made up of minerals, organic matter, water, and air. All right. So not just any one of those, but typically all four. The difference sort of between soils and rock, right, is rock is a large piece, so greater than 2.5 inches in diameter. So if we get a particle that is smaller than 2.5 inches in diameter, that's going to be a gravel. So a soil. So anything that's greater than 2.5 inches in diameter is still rock. All right. So we said that soils have organic matter. So what is organic matter? So organic matter is number 1 and number 2 here that we're going to talk about. So number 3 is if you're going to the grocery store and you want to buy tasty foods. But for soils, we're looking at number 1 and number 2. So number 1 is it's a decomposed living organism. So anything that has died and then been decomposed by nature. That often gets broken down into what you see here, and then also number 2, all that decomposed stuff has to contain carbon. So carbon is what gives it that dark color. So organic soils are pretty easy to point out. Usually they have a dark color and the smell of decomposition. All right, so we know that soils are made of the solid matter, right? We have minerals and organic matter, and then but those pieces, they don't all fit together real nicely, right? So let's take a look at this this soil graphic here, right? So here we have sort of a close-up of a soil sample, right? And it's made up of all these little particles here. Right, so we got 9 little particles, and those particles they don't fit together perfectly. It's they're not perfectly square U-Haul boxes that you put in the back of the truck and you fill it up perfect, right? These are all different shapes and sizes because nature isn't perfect, and things don't always get broken down exactly the same way, right? So here's our mineral and organic pieces. They don't fit together perfectly, and we can see that there's these spaces in between the particles, right? So we call those spaces in soils, we call those voids, right? And those voids are typically filled with either one of 2 things, either air or water. They can sometimes be filled with oil, and if you got a lot of that on your property, you could be pretty rich. But for this class, we're just going to deal with air or water. All right, so let's assume that this soil little graphic here is equal to 1 cubic yard of soil. And if we did an analysis of the volumes of this 1 cubic yard of soil, we'd end up with this gray bar of solids and this white bar here of voids, right? So if you add up the volumes of both of those, we end up with 1 total cubic yard of soil. So let's see how that soil composition further breaks down. All right, so we break that composition down a little further, and most of that soil, those solids are minerals. We have some organic matter, we have some water, and we have some air. And this is probably pretty typical. If you just went out and dug a hole somewhere, you'd probably get a pretty similar composition of soil. Now, big question: can we change the soil properties uh, by only changing the what's in the voids, by just changing the air and the water in the voids? And the simple answer is yes, we can absolutely change the properties of the soil by changing the what's in the voids. So here's some ways we can change what's in the voids. So we can compact the soil, right? So in compaction, we remove air from a soil. So when we do that, we make the soil more dense, right? And we still have the same amount of minerals and organics and water. We have less air, so we have the same amount of mass and a smaller volume, so denser soil, right? We can also, if this is a fine-grained soil, we can consolidate the soil. So in soil consolidation, we have saturated soil, so there's no air in there anyways. But in consolidation, we remove water. So again, further compacting the soil. Right, so consolidation is removing water from the voids. So still same amount of minerals and organics, but now we've reduced the amount of water. We can always excavate a soil, right? So if you go excavate a soil, what you end up doing is adding air to the soil, right? So now we've increased the volume of the soil by adding air to the voids. And then another thing that can happen is we can also add water to the voids, and we call that swell. So still have, in all these depictions, we still have the same minerals, right? And we've only changed the voids, and all of these soils would have vastly different properties. Some are better for engineering purposes, and some are worse for engineering purposes. We call these relationships between the solid matter and the voids in a soil phase relationships. So when we talk about a soil's total volume, we are talking about the volume of the solids, the water, and the air. So the total volume of a soil is equal to the summation of all of these. When we talk about the weight of a soil sample, we talk about the weight of the solids and the weight of the water. So the total weight is equal to solids plus the water. We ignore the weight of the air because it is negligible in the overall mass or weight of our soil sample. And then we have two different types of relationships to the weight and the volume. We have the unit weight, or gamma soil, which is the total weight divided by the total volume. And then we have the gamma dry, so just analyzing the solids, right? So the weight of the solids divided by the volume of the solids, right? So our gamma dry has no water in it, right? So this gamma soil is going to have water. All right, so let's do a quick question. All right, so we've got some soil samples. Each are 1 cubic yard. Which one is going to weigh more, A or B? If we just analyze these real quick, A and B have the same amount of minerals and organic matter and the same amount of voids, but B, all of the voids are filled with water, and A, some of the voids are filled with air. So soil sample B is going to weigh more, and soil sample B will also have a higher unit weight than soil sample A, even though they have the same amount of minerals, because B has more water in the voids, it weighs more, same volume, so higher gamma. Of note here, if all the voids in a soil are filled with water, we call that soil saturated. So soil B is saturated, right? So it can't gain any more weight from water because all the voids are already filled with water. So that is as heavy and as soil B can get, and the highest that the unit weight for soil can get. So we have another relationship that we use for soils. It's called the void ratio. So the void ratio essentially just tells us how much of our soil is voids, right? Because remember, the soil is not just the solid stuff, it's the solids and the liquid and the gas, right? So we do want to know how much of our soil is voids, because the voids have a direct relationship to the strength of a soil, which we'll see here in a few slides. right? So void ratio E is equal to the volume of the voids divided by the volume of the solids. So we're comparing the voids to the solids, and typical values for void ratio get down to about 0.3 and up to about 1. I mean, they can go higher and maybe a little bit lower, but 0.3 is about as low as it goes. We can also define how much water is in a soil by using the water content, or W. So this is an important factor that you'll need for soil classification, is how to understand what the water content is and how to calculate it. But the water content is simply the weight of the water, and again comparing that to the weight of the solids in the soil. So not comparing to the total weight, because the total weight is the water plus the solids, so then you'd be comparing water to water and solids, so that doesn't quite make sense. So water content is the weight of water divided by the weight of the solids times 100%. Typical values for water content in soils, for inorganic soils 0 to 50%, but organic soils we can see values up to 1200%. So that means there is 12 times more water than solids in some of our organic soils, and that can have some real consequences when it comes to the strength of the soil, because instead of having soil particles hold you up, that's only water holding you up. So yeah, water and voids have major impacts in a soil strength, almost much more so than the actual mineral content. So water and voids are really where the rubber meets the road in soils and soil strength. All right, so we've got some examples for voids. We'll go through this. So what we have here is we have two soil samples, A and B, and we have a little cross section here so we can see 6 particles in each of these samples. So A and B. So let's go through these questions here. So question 1 is, which soil sample is denser or more dense? Right, so density has to do with how much void space is in the soil, right? Lots of void space, less dense, less void space, more dense, right? So A has these big giant voids between the particles, whereas B, these voids are much smaller. So soil B is our more dense soil. All right, question 2, how can we make sample B even denser, right? So we can't compact these anymore, and we can't fit any more big particles in here. So this is about as good as it gets, unless of course we get smaller particles to fill the void spaces in B. So if we got some smaller particles, we could put those in the voids there, right? So that would make it more dense, right? So that's one thing that is important in soils, is having a variation in grain sizes, because you have lots of variation. You can put particles in between the void spaces of other larger particles, right? And even these voids, we could fill these voids, with some even smaller particles and try to fill up as much space as possible. All right, so we can make sample B denser by adding smaller particles in between the larger particles. All right, so question 3, which soil is going to resist more force and why? So let me erase these. So we're just going to assume it's just the original condition, so we don't have these red particles anymore. So we're applying a shear force on these particles. So the force is coming in from the side here, shear force. And remember, these particles are all on Earth, so we have gravity acting down. So we need to figure out which soil is going to resist more force and why. I think your intuition tells you it's going to be B, but the big question is why. So let's look at the why. All right, so let's focus on firstly the starred particles, right? So in A, the starred particle, how many other soil particles is it touching? So it's touching 1, 2, 3. So we'll do that. So 1, 2, 3. right? In B, looking at our starred particle, then it's now touching 1, 2, 3, 4 particles. Now, granted, this is two-dimensional, so it's not exactly 3 and 4 if you go into three-dimensional space, but for the cross-section, this is good enough. It shows that in a denser soil, each particle is in contact with more particles, right? So more contact points, right? So we have more contact points for that one particle than this one. So we have more friction between the particles. So soil sample B is A, going to resist more force just because of friction between particles. All right, so that's one reason. What is the second reason? Well, that big green gravity arrow might be an indication of the second reason. So if you apply this force here at A, these particles will just all shift that way and they'll just fall nicely into place here, right? So they'll fall into place with gravity. So gravity helps in A. In B, for these particles, these top particles to move, they actually have to move up, right? They have to go up and over these other particles here, right? They have to go up and over those particles. So these actually have to work against gravity. So gravity also helps keep soil sample B in place, helps resist more force. So the second one is gravity also helps. Right. So actually, in some soil tests, soils are known to actually expand as you apply a vertical force because of this phenomenon where the soil particles have to jump up and over the ones below them to move. So, interesting phenomenon. All right, so let's talk a little bit more about voids. So we know that voids have major impact to the strength and properties of a soil. So let's talk about some ways to get rid of those, right? So there's two main methods to get rid of voids, compaction and consolidation. So compaction and consolidation. So in compaction, we use mechanical processes to basically squeeze the soil and push the air out. So vibration methods or steam rollers, all those kinds of things are used to compact soils. So we're just trying to push air out of the soil in compaction. So consolidation is a totally different process. Consolidation we use on fine-grained soils or cohesive soils. And in cohesive soils, water doesn't flow very easily. So consolidation, we just apply a large static overburden pressure, which is usually just a large pile of soil on top of the soil that we're trying to consolidate. And that applies the overburden pressure, and that slow static pressure forces the water out. Usually there's some drains installed so that water has somewhere to go to drain off. And then we remove the water in consolidation. So consolidation is not for removing air, it's for removing water for fine-grained soils, and compaction is for coarse-grained soils to remove only air. All right, so here's another graphic kind of talking about compaction and consolidation. So here's a picture of consolidation setting up for it. So all these white pipes here, these are called wick drains, and so you install wick drains into the soil, and then what they're going to do next is they'll come and they'll put a big giant mound of dirt on top of this site here, and that dirt will apply pressure to the soil below and force the water out of the wick drains, right? So that'll consolidate the soil. Another way you can consolidate soils, if it's just you need a little bit of consolidation on the surface, you can use this sheep's foot roller here. And compaction is just a little more straightforward. You have all these different methods here for compaction, and deep dynamic compaction is pretty cool. Go ahead and watch that video. It's only 30 seconds long or so. That's used to compact soils in a localized method. All right, so now that we understand the phase relationships of soil and how voids and solids affect the density of a soil, we can talk about how to do some earthwork calculations. Before we get into that, we'll talk about some earthwork terminology that we typically use. So we use three different terms for soil in three different states. So when a soil is in its natural state, we say that soil is banked. So if we were to take a volume of that soil, we would call it a banked cubic yard, or BCY. So that's just a volume of soil that's in its natural state. So natural state would just be, you go out to wherever your site is that you're going to build or excavate, and that would be the BCY soil there. So we're going to take that soil out of the ground and we're going to loosen it up a little bit, right? We're going to add some air voids. So that loose state, we call that volume the LCY, or loose cubic yards, right? So as we loosen up the soil, the density of the soil is going to go down. And then eventually we're going to take that soil and put it on a site somewhere and compact it. So we call the compacted volume the compacted cubic yards, or CCY. Right, so in our CCY, we're going to remove our air voids. So it's going to be possibly our most dense state of soil. So what's the relationship between BCY, LCY, and CCY? Well, we have changed the number of voids in each of these three conditions, but one thing that has not changed is the mass or weight of that soil. So we can say that the unit weight banked is equal, or times the volume banked is equal to the unit weight loose times the volume loose, which is equal to the unit weight compacted times the volume compacted, which equals the total weight. So the weight of our soil never changes between these three states, just the unit weight, and by changing the unit weight, the volume also changes. So let's look at this picture here. Kind of shows how that BCY, LCY, CCY transition, right? So we go and we dig up some soil over here, and then we put that soil in this truck, and now the soil takes up a little bit more volume than it did before we excavated it, and then we dump that on a site somewhere, and we compact it, and now its volume is a little bit smaller than it was before it started, but the weight at all of these stops is the same. So if we pull 1,000 pounds of soil out here, we're going to put 1,000 pounds of soil there. It's just that the volume banked and the volume loose and the volume compacted are going to be different. So these relationships here are general, so each problem will dictate the relationship between the volumes and the unit weights of those. So those are just generalized relationships, not actual ones, so don't use those in your calculations on the homework. All right, so now that we understand the relationships between the banked, loose, and compacted states, we're going to need to figure out how do we calculate a volume of something in the ground, especially if that volume is non-linear like most things in the ground are. So the way we do that is we use what's called the average end area method, right? So the average end area method says that the volume of a complex shape is going to equal to the average of the cross-sectional areas at the end of that shape, so A1 plus A2 divided by 2, right? So that's the average of those two, times the length between those shapes, length between those cross-sections, right? So if we look down here on the bottom of the page, we have a small shape with two differing cross-sectional areas. And kind of walking through, if we looked at those two cross-sectional areas, we see A1 and A2 are not the same. But if we add those up and take the average, we get this average cross-section that represents sort of the whole of that shape, right? And if you multiply that times the length, then you get the volume of that shape. So yeah, if we have a nonlinear shape, we might have multiple cross sections. So you would end up doing the sum of volumes if you have multiple shapes. So this might be, A2 plus A3 over 2 times L2, right? If you have multiple shapes. So you just find the volume between for each section, and then you just add those up if you have multiple cross sections. All right, so here's some examples for determining volumes of soil based on loose or banked or compacted states. So go ahead and watch the example videos on this. And here are some examples for using the average end area method to find volumes of soil excavations. So note in number 2 here, we have 1, 2, 3 different sections. So you'll have to use this average end area method 3 times, and then take the sum of those 3 values to get the correct answer. All right, so here's the review. Thanks for watching, and hope you learned something great.